Good morning, students. This is KG Misra. I hope all of you are well and fine and studying hard. I have come today with the next part of the video for class 12 on chapter magnetic effects of current. Okay. Till the last class we have discussed, that is online class, we have discussed about the force acting on a charged particle moving in a magnetic field. Here we are going to discuss about this force on current carrying conductor placed in magnetic field. So, how this force acts and why this force acts on a current carrying conductor when it is placed in a magnetic field. What is the reason for this? See, reason is that see, if there is a magnetic field, that means there is somewhere there is a magnet is there, because without magnetic field it's not possible. So here somewhere we have got a magnet. Okay. That's why it is creating field in this region. Okay. Now, when you are placing in this magnetic field, suppose here magnetic field is there, and this magnetic field you are placing a current carrying conductor. So what we know, a current carrying conductor behaves as a magnet. So that means this is also a magnet. Okay. And this is a magnet. What we expect between two magnets? Either they will repel or they will attract. Okay, that means they will apply force on each other. Yes, and that is the reason when a current carrying conductor is placed in a magnetic field, it experiences force. I think you got it. Okay, now the next question which creeps in our mind, that how much force it is going to experience, the current carrying conductor, when it is placed in a magnetic field, then how much force it will experience, the quantity. For that quantity part, let's see ahead, let's move ahead. Okay. Now what I am going to take, see, we already know that if a charge is there, Q, and it is moving with velocity V in a magnetic field B, then it experiences this much force. Okay. Now if the charge is an electron, then the force will be like this. Okay. Let us mark this as equation number 1. So you can see this force is acting on an electron is given by this. Okay. Now suppose we take a conductor. This is the conductor I have taken. You can see this is the area of cross section of the conductor. Area of cross section is A and length is L. Okay. Now what we will do, let the number of electrons, rather free electrons, okay, we will write here free electrons, free per unit volume, volume is n. So what we have taken? We have taken the number of free electrons per unit volume is n. Then total number of free electrons in the conductor A will be, let it be capital N. Okay, and capital N is equals to, obviously per unit volume how many electrons are there? Small n. So what is the total number of free electrons in this conductor? Obviously this number of electrons per unit volume into the volume of the conductor. But what is the volume of a conductor? Say conductor is in the cylindrical form, so its cross sectional area into its length will give its volume. So what we can write? NaL. This is the total number of electrons. Okay. Now let us mark this as 2 and let us mark this as 1. Okay. So from these two equations what we can get? We can get the net force acting on this all the free electrons present in this conductor. Okay. So see, I'm going to rub this upper part so that we can get proper space to write. Now, from equations 1 and 2, no, what we can get from equations 1 and 2. What we will get, just see, we will get rather I'm writing F instead of small f. Why? Because this is the net force and minus is there, okay. And now we can put the N, this small e is there, V cross B, okay. But what is capital N? That is equals to, you can see equation 2, it is small n A L E V D, this is V D, okay. The drift velocity, this velocity is what? This is drift velocity in case of electron, okay. So we are getting V D cross B. That is the net force acting on all the free electrons present in that conductor. Now, if the force is acting on all the free electrons present in that conductor, then obviously, who is experiencing that force? Obviously, the conductor is experiencing that force because electrons are there in the conductor. Okay. So, this is the force felt by the conductor. Okay. So, what we can write? So, F is the net force acting on conductor. Okay. Now, see, we can see from here one thing is visible to us, and that is what is the expression of current in terms of drift velocity that we have already derived in a third chapter. Okay, that is current electricity. So we know that, but I is equals to NEAVD, that we know very well. So from here, what we can do, we can place this, okay, this we know. Let us mark this equation number 3, and this equation we can write in scalar form, that is minus NALEVD B sin theta, where theta is the angle between direction of drift velocity and direction of magnetic field. Okay, theta is angle between direction of VD and B. Okay. Now, let us mark as equation number 4. And now we want to do the substitution part. Okay. So from equations 3 and 4, what will get? F is equals to, minus is there, okay, N E A V D, that will give us I, only L is left, so L I, okay, or we can write I into L, and what is else is left? That is B sin theta. Okay, this we are getting. But my dear children, we know that no, the direction of current is opposite to the direction of drift velocity. Okay. So here, what we need to write, that is a minus sign. Why? Because VD has opposite direction. To that of current. Okay, because VD has opposite direction to that of current, that's why we are putting a negative sign. Okay, now this negative will become positive. So what we get? Should I rub the upper part? I hope you have done. Okay. Now, once I have removed it, what we get, see, we get F is equals to Minus is gone. So we have got I, L, B sine theta. Now see, F is a vector quantity, B is a vector quantity. And what about this? Is this a scalar quantity? No. Actually we call it current element. Current element. That is I, L. This is a vector. And direction of this vector is along the direction of current. And magnitude is the product of the length of the conductor and the current. Okay? Clear? It's directed along the direction of current. And magnitude of this vector is the product of length of the conductor and the current. Okay? Now, so what we can do here, if this is a vector and this is also a vector, and result also we are getting vector, then we know that between two vectors, only two products are possible, cross and dot. But in dot we get the result scalar, here we are getting vector. So this indicates that the product should be cross product. One more thing, when we are taking cross of two vectors, that is A cross B, then we get A, B sine theta. So presence of sine theta also indicates that the product is cross one. So what we can write? F is equals to I, L vector cross B. Okay. So this is the expression for force acting on a current carrying conductor, which is carrying current I and having length L, and is placed in a magnetic field, external magnetic field B. Okay. If we are interested in magnitude, then what we can write? ILB sine theta. What is this theta? This theta is angle between that is IN, or we can write between direction of current and magnetic field. Okay. So there of the lower part. So theta is the angle between direction of current and direction of magnetic field. Okay. And this is the expression for magnitude of the force acting on a current carrying conductor. Okay. When it is carrying current I, having length L, and placed in a magnetic field B, such that the direction of current and direction of magnetic field is making angle theta between them. Okay. Now, case 1. We can take the cases. Case 1. When theta is equals to 0 degree, then what will be the force? Let's see. We know that F is equals to I, L, B sine 0, because 0 degree means 0, sine 0. Sine 0 is how much? It is 0. So what will get? Force is equals to 0. Okay. Now case 2. When theta is equals to 90 degree or pi by 2, then what will happen? Let's see. Force is equals to I, L, D sine 90. So what will get? See, sine 90 is how much? It is 1. So as sine 90 is 1, so what we can get? F is equals to I, L, B, and this is the maximum force which acts on a conductor when placed in a magnetic field. Okay, clear? So this is the minimum force we can see. This is the minimum force, and that is the maximum force. When the minimum force will act? When the direction of current and magnetic field both are along the same direction, then force is 0. So is it for only same direction? No. Even if theta is equals to 180 degree, then also what you will find, then also you know sine 180 is 0. Okay, and then also the force will be minimum. Okay, and for 90 degree or 270 degree, because 90 and 270 you know that's similar, so you will get the maximum force. Okay, now we are going to talk about the direction part. The direction of the force is given by the Fleming's left hand rule. I think you might remember that, but I will tell you again. Okay, the direction of force. Should I rub this upper part, my children? You have done it? Okay. As far as direction of the force is concerned, so it is given by, see, so direction of the force on a current carrying conductor placed in a magnetic field is given by Fleming's left hand rule. Okay. Now see, this left hand rule you have studied in class 10th. Again we can recall it. Okay. See, what we have to do, we have to take our left hand and we have to make it in this way. The thumb, the index finger and the middle finger. We have to keep them mutually perpendicular to each other. See, you can see this thumb and this index finger, it is making 90 degree. You can see this middle finger and the index finger, it is making 90 degree. You can see this angle is also 90 degree. Okay, so it is 90 degree. You can see visible to you. Okay, so all the three fingers must be perpendicular to each other. That we call as mutually perpendicular. Now, remember one thing, this thumb indicates the direction of force only when your index finger is coinciding with the direction of magnetic field and middle finger is coinciding with the direction of current. But many times students used to forget that which finger represents what. So for that, there is a very easy trick. See, the pillar of the family is father and then mother and then the child. Okay, so F for father, M for mother, C for child. F for father means F for force, M for mother means M for magnetic field, C for child means C for current. Okay, F for father, force, M for mother, M for magnetic field, C for child, so C for current. Okay, in this way we can remember. So it is given by Fleming's left hand rule. If you want to write the statement, then you can write, please. It states that when the thumb, index finger and the middle finger of left hand are stretched mutually perpendicular to each other, then such that mutually perpendicular to each other, such that the index finger is along the direction of magnetic field, middle finger is along the direction of current in the conductor, then the stretched thumb gives the direction of force acting on the conductor. Okay, so this is the statement of this Fleming's left hand rule. Now, how it is used, that we are going to discuss with the help of a situation. Suppose here is a magnetic field. What does this direction indicates? Let me tell you first. This is indicating the direction of magnetic field B. See, you might have seen the mathematical serials, no, in the television. So you might have seen the arrow. Here it looks like this, and here they had got four projections. Okay, why? So that it can be properly fixed in the string of the bow, and so that it can be pulled properly. Okay. Now, when this arrow is coming towards you, then what you will be able to see? Only this point, that is, only point will be visible to you, okay, which we represent sometimes like this. So, when this point is there, that means arrow is coming towards you. That means direction of magnetic field is towards you, if it is representing magnetic field. If it is representing current, then current is coming towards you, okay. Now, when this arrow is shot into the board and it penetrates inside the board, then what will be visible to you? Only this will be visible to you, the back part. So when it is like this, that means the direction of the magnetic field is inside the board, if it is representing magnetic field. If it is used to represent the current, that means current is going inside the board. Okay. So this cross represents inside, okay, away from you, perpendicularly away from you, and this dot represents perpendicularly towards you. Okay. So this is the direction of magnetic field. Now, suppose a current carrying conductor is there, and this conductor is carrying current I in this direction. Now we need to apply this left hand rule to get the direction of force on this conductor. So let's see. This is the middle finger must be along the direction of current. Okay. This is the index finger, it should be along the direction of magnetic field. See, magnetic field is inside, so my finger is pointing towards inside. This middle finger is along the direction of current. Okay. Now the direction of thumb is giving the direction of force on the conductor. You can see this thumb is giving the direction of force. That means force on this conductor will be in this direction. Okay. Suppose in the same magnetic field we have got a conductor which is carrying current in the opposite direction. Then what will happen? Okay. So in this case the current is in this direction. Okay. So now current has got opposite. Okay. But what about magnetic field? It is inside. Okay. It is inside. So what we can do? See, this is the current is in that direction. Okay. It's better to change your position rather than just twisting the hand like this. Okay. Because in that you may make mistake. Okay. So you can see this is the middle finger indicates the direction of current. Okay. I am coinciding with the direction of current. The index finger is along the direction of magnetic field. You can see very well it is along the direction of magnetic field. It is going towards the board. Okay. Inside the board. And the thumb indicates the direction of force that you can get. Okay. So direction of force is downward. Okay. So in this way we can use our left hand, okay, according to the Fleming's left hand rule to find the direction of force on a current carrying conductor when placed in a magnetic field. Okay. Okay. Now let us take up a question. Okay. See, this is the question, and in this question there is a conductor, okay, which is placed along the direction of x-axis, and its length is L, and it is carrying current I along the direction of x-axis. Okay, positive direction of x-axis, I should say. Okay. Now in this region there is a magnetic field. Magnetic field is B is equals to B naught I cap plus J cap plus K cap. Okay. This is the magnetic field in this region. Now the question is that how much force acting on this conductor, and what is the direction of force? That's what we want to know. Now see, as the current is flowing along the positive x-axis direction, so can we write that IL is equals to, we can write IL I cap, because it is along the x direction, and for x direction we know very well that the unit vector I is used. Now we know that force F is equals to what? It is I L cross B. So as we know that, see, this is the question we are going to take. Okay. In this question, a conductor is there of length L, and it is placed along the x-axis. Okay, and it is carrying current I. Okay. Length of the conductor is L, and you can see the direction of current is along the positive x direction. And see, the magnetic field which is given in this region, that is B is equals to B naught I cap plus J cap plus K cap. Okay. Now as the current is flowing along the positive x-axis direction, so what we can write? Can we write this IL vector is equals to IL I cap? Why I cap? Because I cap represents positive x-axis, and our direction of current is along the positive x direction. Okay, that's why. Now in order to find the force, what we know that formula is F is equals to IL cross B. So IL we can write in this form using I cap, and B naught plus this is bracket I cap plus J cap plus K cap. Now we need to take the cross product. Okay. While taking the cross product, we can keep I outside. We can okay. We can take this L. Okay. I cross I is 0. Okay. So we have right here 0. Then I cross J. I cross J is what? I cross J is K. You might remember that circle, okay, that is I, J and K. So I cross J is K. If you are going along the clockwise direction, then it is taken as positive. If you are going anti-clockwise direction, it is taken as negative. Like I cross K is minus J. K cross J is minus I. Okay, and J cross I is minus K. Okay, if you are going in this way, I cross J is plus K, J cross K is plus I, and K cross I is plus J. Okay, so in this way it is there. So here I cross J is plus K. So we will get K for this,
And what magnitude we are going to have? See, B is multiplied 2 also. B into L. So we can write plus LB K cap. Okay. Now we have to multiply this with this one. So we have to take the cross off with this one. So L and B, that will be there, no problem. L and B. Now I cross K. So I cross K, it is in reverse way. So we will get minus J. So we are supposed to put here minus, and here we need to put J. Okay. So this multiplication is over. We can put here our square bracket. Okay. I'm going to rub this. Okay. Now what we'll get, see here. This is the force. I is there. What we are having on the side, that is LB K cap minus LB J cap. Rather B naught, not B but B naught, because B naught is here. So what we can do, we can take this IL common, sorry, LB common. So ILB, okay. What we are having, this is minus J cap plus J cap. Because this is the order we used to follow. First we write J, Y component, and then we write the Z component, okay, X, Y, Z. That is the order we used to follow. So this is the force in direction as well as in magnitude acting on this conductor. Okay, just note it down. Okay. Now for the magnitude of this force, what we have to do, magnitude of force. So for magnitude of force, we know very well what we need to do. We need to find out the magnitude of this. For that, what we'll do, F is equals to, we can write in this form, no? This also can be written as ILB, okay, minus ILB J cap plus ILB K cap. We can write in this form also. So while taking the magnitude, what we do actually, we square these coefficients of J and K and add them the square root. So in the same way we have to do here, ILB whole square, rather minus plus ILB whole square. So what will we get? ILB whole square plus ILB whole square. This minus is there, no problem. Its square will be how much? I square, L square, B square. And this also will give us I square, L square, B square. So both are going to give the same thing. So what we can write? Can we write like this? 2I square, L square, B square. So when we take the root of this, then as a result what we will get? Let's clear up this part so that I can write the final answer of magnitude. That is, magnitude will be root 2 ILB. Rather, it is not B, it is B naught. Again, I have made the mistake. See, it is B naught, okay. Always I am writing B. See, this happens. So we got ILB naught, okay, root 2. That is the magnitude of the force. Okay, and this is giving representing magnitude as well as direction. That means this much force is acting along the negative y axis. This much force is acting along the positive z axis. Okay, and this is the total magnitude of the force. Okay, magnitude of the resultant force. Got it? So note down. Okay.